Valence Electrons Part 2. So, last time I talked to you about the basics of orbital theory and the valence electrons associated with them, mainly with the s and p orbitals. So today I want to get into the d orbitals and tell you about them. Now, I realize that with a lot of these videos I've been going really quickly through this stuff, but I hope that you've been rewatching them and then testing out some of the theories. Say if you have a textbook, try some of the problems in the back of the book and use some of the stuff I tell you and see if you can actually solve them. And so let's start by just telling you about the orbitals. So last time I taught you the s orbital, which is sphere-like, sphere, s. The p orbital, which is p-shaped, like a peanut. So p orbital, peanut. Makes sense, right? Now, let's get to a weirder one, which looks kind of like this, only it'll be on different planes. This one is on the x and y plane. This is the d orbital. And another form that it will come in is, I am not the best artist, but just bear with me on it. Hey, that looks pretty good. Well, a peanut with a donut around it. So donut d orbitals. And then it has the four spheres in the same plane, and those four spheres are the most common form to see it in. It'll be in the x and z plane, the x and y plane, the z and y plane. Pretty cool stuff, I know. So, those are the orbitals. Now let's scroll on down to my periodic table. And so, I'm just going to put myself here. You have the d orbitals being located right here in the transition metals. So, s orbitals, p orbitals, and d orbitals. And just because I'm going to show you one other type of orbital, I'm not going to attempt to draw this one because, well, it's kind of messy. But I recommend that you look it up. So, the lanthanide and the actinide series, they are f orbitals. And there's really no good way to remember that they are called the f orbitals because they look nothing like anything that starts with the letter f. So if you have time, look them up on Google and see what you find for what the f orbitals look like. There are some cool images as to what they look like. But it's all mathematical probability that gives rise to these orbitals, and they've all been derived from actually a hydrogen particle losing its electrons and forcing its electrons into higher shells. And that's how we come about the shapes of these orbitals, is by the electron probability, which is all a lot of mathematical equation and calculus, which is a lot of fun when you get to that level. So, let's take a look at some of the transition metals. So I've numbered the transition metals. We have 10 transition metals, which means we have 10 electrons in the orbital. Well, when I say that there are that many in the orbital, there is actually 2 electrons in each orbital. So if there are 2 electrons in each orbital, 10 electrons total that can go into the d orbital of d orbitals, that means there are 5 different d orbitals in each shell. Let's put it that way. Yeah, there are 5 d orbitals in each shell. There is 1 s orbital in each shell, and since we have 6 p electrons, that means that there are 3 p orbitals. So I hope that makes sense. And so you need to remember that and keep that straight, that there are 3 p orbitals, 5 d orbitals, 1 s orbital. Now, as far as how many electrons they can hold, the s can hold 2 electrons, the p can hold 6 electrons, the d can hold 10 electrons, and the f can hold 14. So to remember the number of electrons it can hold, just add 4 to the previous. S has 2, p has 4, p, you add 4 to the 2, so you have 6, d has 10, and then f has 14. The number of orbitals is simply the number of electrons divided by 2. So now that that math is out of the way, and we can get into some of the transition metals. Let's take a look at, I'm feeling nickel. So nickel, what is the electron configuration of nickel? Now, an electron configuration is when you have the orbitals and how many electrons are in each orbital. So let's start with the electrons in the top layer. We have the 1s2, because it's fully filled, there are 2 electrons in it, 2s2, 2p6, yep, going well so far, 3s2, because we're right here in the 3rd level, and then there's no transition metals, so we continue on to the 3p6, and now we're in the 4s section, so 4s2. Now this is where it's going to get kind of tricky, because it's 3d and nickel is 8. So it goes back a number. So why does it go back a number? Well, this is the way that I tend to think about it, and this rule does hold true for valence electrons. And that is that the number of its, well, in higher mathematics we're going to talk about nodes, but to keep it simple, it is that with each increment of the increase of the prefix, when the prefix increases, we think about it as adding a new type of orbital. And so the 3 is the next prefix. Since 1 gets the s, 2 gets the p, 3 will then get the d, even though it's not in the 3rd period of the periodic table. So you just have to remember it in that fashion, and I am currently rolling my chair over my cord. Alright. Now, when we continue to think about it, when we get into the 5 period, the 5s will then go compatible with the 4d. And then, to remember this, after the 3d, 10, we will then go back to p, the 4p6. And that's the configuration of krypton. I don't have the elements perfectly memorized, so... But this is the configuration of nickel. Now let's make a shorthand out of this, because this is a lot of stuff to write down, right? So, well, this is a complete shell. This is helium's shell. So we can shorthand it and put helium as a substitute for that, but that doesn't save a lot of space. Right here is neon. So we can put neon whenever we get this far. And we don't have to write hydrogen, because hydrogen is a part of neon. So we can write neon. Now, if we go even further to here, we can write argon. Because everything up to that point reflects argon. And so we can shorthand this entire thing to argon in brackets 4s2 3d8. Now it's time to teach you guys a whole new rule. So I'll leave that up there for a minute. And that is that when all of the orbitals are half filled, they are happy. They find themselves to be stable when they are both filled and when they are half filled. So, well, let's take a look at some orbitals that want to accomplish being half filled. Let's take a look at manganese, which is, well, at chromium, which wants to be like manganese because manganese has all of the orbitals, all the d orbitals are half filled. But krypton doesn't have that. So what is it going to do? It's going to steal an electron from its s orbital. So we have argon as the shorthand, and then we have the 4s2 3d4. Well, the s is full. The d isn't half full. So the d is going to force its way to be half full, but also make the s orbital half full. So then what we get is this little number. This will also happen with copper, because copper wants to get that full level at 10,